Okay, for this problem, we're told that the elements of the lower arm are shown in the figure, and the weight of the forearm is 5 pounds, and it has a mass center here at G. And notice how G is located for us. We're given this 55-degree angle that is really measured between a line that extends down the forearm, so to speak, and this vertical. And then we're given a distance of 6 inches measured in that same direction. So it's located a little differently in this figure compared to other things. But it's 5 pounds, and then we want to determine the combined moment around the elbow pivot at O for the weight of this 8-pound sphere and the forearm itself. Then we need to answer the question what the bicep tension needs to be so that the overall moment about O is 0. So this is kind of a little different way to get to an equilibrium question, but we're doing it with 2 different moments. All right, so let's establish a sign convention here. We'll just take counterclockwise positive, and what we want to do is simply compute the moment that this 5-pound and 8-pound force make around point O. So the moment around O is equal. We can just use a scalar approach. So the 5-pound force, if we have a counterclockwise positive, by the right-hand rule, the way this force acts around point O, it's going to create a clockwise rotation around point O. We would need to have the horizontal distance that point O is from the line of action for the 5-pound force, and that should be easily seen as 6 times the sine of 55 degrees. So we're going to have a minus 6 times the sine of 55 degrees multiplied by the force, and the force is a 5-pound force. And then we can look at the 8-pound force, and the 8-pound force is easily seen to act at a distance of 13 inches away from point O. Again, horizontal distance to the line of action for the 8-pound force as measured from point O for the moment arm. Moment arms must be perpendicular to lines of action when you use this scalar approach. So it's also going to create a minus moment, but it's 13 times 8. And if we compute this number, we get a minus 128.6 pound-inches. So we could write that the moment around O would be equal to a positive 128.6 pound-inches. And we've removed the minus sign because we write that it is a clockwise moment. Now, they ask us what the tension T needs to be so that the overall moment around point O is equal to 0. Well, obviously, for the moment around O to be equal to 0, then the moment which T makes about O must be 128.6 pound-inches counterclockwise. It's got to be able to undo the moment made by the forearm weight and the weight of the sphere. So, moment around O is equal to 128.6 pound-inches. T is going to put a counterclockwise moment around point O, and it's a distance of 2 inches away. But the right-hand rule shows us that it will make a counterclockwise moment around O. So 128.6 pound-inches, and let's drop the units for right now, would be equal to 2 times T. The moment arm times the value of the tension. And we would find that T is equal to 64.3 pounds. And that's it. So this is like an equilibrium problem, but we've looked at it from the perspective of finding the moments of 2 different sets of forces. And that's it for this question.